the probabilities for the different values of x have to be at least 0 and less than 1 when expressed as a decimal. And furthermore, the total has to be exactly equal to 1. So when we're asked to verify if this is a discrete probability distribution, well, although there's only 5 values, I'm going to bring up the calculator. That's going to be showing up in a moment, but in the meantime, clearly none of these are negative, so all of those values are at least 0, and none of them are bigger than 1. So that part's good. We need to see if the total is exactly equal to 1. So here we go. 0.342. Let's see here. All right. 0.342 plus 0.399 plus 0.119 plus 0.056 plus 0.084. And we do get a total of 1. Inclusive means that we could have exactly 0 or exactly 1 for the probability of a particular value of x. Now, graphing this, it looks kind of like a histogram, but it's not exactly the same. We've only got just a single vertical line segment above each value of the random variable. And notice how from 0 to 1, the value increases a little bit. Then we have a sharp decrease, another decrease, and then an increase. So the only place I'm seeing that is here with part D, and getting more specific. Right here, 0.3 something. This one's 0.3 something, but a lot closer to 0.4. 0.119, that's just a little bit above 0.1. 0.056, this is, it looks like it's a little more than halfway between 0 and 0.1, etc. So I'm going to choose choice D. Coming up with the mean. Well, first of all, I'm going to download this to Excel. And I want to show you the concept behind calculating the mean of a discrete random variable. Okay, notice that all of those probabilities were to the thousandths place, 3 places out. So suppose that we perform this 1,000 times. Multiply each of these by 1,000. If the experience of doing this 1,000 times would, if the experimental probabilities exactly matched up with the theoretical probabilities, then we would expect this to exactly happen. However, it's usually, you'd have to do this more than 1,000 times to get things to match up. However, if I then find the mean of all of these, remember on Excel, just tell it the average, tell it the column C and row 2 down to row 5 in the same column. Oh, it's going down to 6. Okay, well, that would be 200 out of 1,000 times. So the mean of the random variable should be 0.2. Now I'm going to check that, and then I'm going to show you a shortcut after that. So let's see if we get agreement with 0.2. Okay, backing up. Needed to give myself a reminder, I guess. Well, that 0 is showing up 342 times, but when you add 342 zeros, you're just adding 0. And why didn't that take? Well, the thing's acting a little funny on me here. So I'll do this for the value of x equaling 1. That happens 399 times. So when computing the mean, we'd be adding up 399 ones, and then 2 times 119, that would be adding 119 twos, you get 238, and so on. This one should just simply be 0. So when we add up the other 4 and add up the 0, we get this for a total, and that's what you would be dividing by 1,000. So I should not have been doing that here with the frequencies. All right, so we should have 1.141 for the mean. Okay, I've got it typed in. It says do not round, checking the answer, and now it's good. Okay, well, what else could we have done? Our other option here, which would be better, would be simply, since these frequencies divided by 1,000, well, here, let me put something on the board. So what I did there a moment ago was to calculate mean in a more traditional approach, doing all the adding and then dividing up by the total number of scores, in this case, by the 1,000. Well, if I put it this way instead, frequency over total of frequencies, that would be giving us a relative frequency, and so an experimental probability. So x times p of x, take the sum of all of that. Let's see what that looks like. So let's get rid of these. Do the multiplication of score times probability of that score. Do that for each row. Add them up. No division needed. It's baked in there because we've got these probabilities being like relative frequencies. There's the 1.141 again. Now, I believe this next part is along the lines of the law of large numbers. The more times that an experiment is done, so increase the number of experiments, and I only see that coming up in part B. As the number of experiments increases, the mean of the observations will approach the mean of the random variable. So when I was saying do that 1,000 times, I was using those theoretical probabilities like experimental probabilities when I should not have been. But it got the point across. Now, standard deviation. There are two equivalent formulas. I'm just going to show one. You've seen standard deviation before, and this looks similar then with the no need for division, because just like here for the mean of the random variable, the discrete random variable, the division is baked in right here. So we're going to take score minus mean, square it, multiply by the probability for the respective score, get the sum of all of that, and then take these square roots. So let's see here. There we go. All right, so each score equal sign, score in the first column minus the mean. We want to keep going to the same row, so I put a $ in front of that 7 there. Put parentheses around that, square it, and it probably doesn't need it, but I'll put another set of parentheses before I type the multiplication, multiplied by the associated probability for that score. And there's probably some rounding going on. I don't want to round it any further than it needs to be, so I'm leaving everything unrounded until possibly the end, depending on what they ask for. So now that's done. Score minus mean squared times probability of that score for all 5 scores. We want the sum of that. And the square root, which I could put all that into a single line here by putting square root parentheses around that, SQRT. Okay, let's see where they want it rounded to. They want this to just 1 decimal place, the 10th place. And so after the 10th place, we've got a 9 in the 100th place. That's going to round up. So let's try out 1.2. And it's good. Now this second to last part is just asking us to read what's the probability that a randomly selected student has a parent involved in 3 activities. So 3 activities, X was the score of how many activities. The probability is 0.056. Now this last part, it's the probability the randomly selected student has a parent involved in 3 or 4 activities. We need to add those. And in the thousands place, 4 plus 6 will give us a 10. So carrying into the hundreds, 5 and 8 is 13, 14. I think we're looking at 0.140 or just 0.14. All right, it's good. More examples shortly.